right, so we can start now. Good morning, everyone. So yesterday we talked about frequency domain approach. Now we will talk about time domain or state space approach for control systems. Let's start with definitions. The really a central definition for this approach is the concept of a state. Right? Over there, Laplace transform or S variable is the central approach. Here is central point. Here is the state. A state of a system at time t0 is defined as the minimum amount of information that, together with the input for all t greater than t0, uniquely determine the system. In other words, how much information you need to have at this given time such that the history of the system is stored in this information, in this set of information. That is called the state. So from this time on, what you need only is the input. Everything else is already stored in that variable. We call it a state. So for instance, for a linear time invariant system, you will see in a moment, but you might even can be able to imagine now. For a linear time invariant system, state space representation is x dot equal ax plus bu, and the output equation is y equals cx plus du. So if you represent the system equations in this form as first order differential equations, a number of differential equations, then these equations are called state equation, and then the equation that generates the output is called the output equation, and these all together they are called state space equations. And here in general, A, B, C, and D, they are matrices, which phi is called the fundamental matrix or a state transition matrix. Now, if you look at this equation, this shows the solution of this system. Now, the integral is from 0 to t and depends on the input, u, and all the information before t equals 0 is stored in this x0. So this solution really satisfies the definition of the states that we just said. So if you represent the equations of the system in this format, then x of t will satisfy this definition because the solution is this one, and this solution clearly, if you look at the solution, you will see that this solution satisfies that definition. Okay, now you may say, what is the relationship between state space equations and transfer function? Just for the sake of curiosity. If you take Laplace transform from both sides of this equation 4, 1, then you will come into these equations, right? And then if you calculate the output, eventually your output will be this matrix into U plus another one into initial condition. So now in transfer function approach, we do not care about initial conditions. What we care is the only relationship between input and output. So this is the transfer function. In other words, if you have A, B, C, and D, then you can calculate the transfer function. So that's the relationship between A, B, C, D, or the state space, and transfer function. And basically, if you want to use MATLAB, MATLAB has two commands, state space to transfer function and transfer function to state space. So if you have your system in a state space, it can translate that into transfer function and vice versa. Okay. Now, what played the main role in transfer function was the poles of the transfer function. Here you will see, and I'm going to prove quickly, that eigenvalues of this matrix A play the same important role, and even more. eigenvalues of matrix A. Eigenvalues, definition of eigenvalues, you know, AV equals lambda V. Lambda is a scalar and V is a vector which is non-zero, right? So that equation becomes this equation, lambda I minus V. And then for this equation to have a non-zero solution, determinant of this matrix must be 0, right? So determinant of this, which gives you a polynomial function, let's say like this, equals 0, that gives you the eigenvalues of this system. Now, if you go back to the transfer function here, we have C Si minus A inverse into B. And you all know when you want to calculate inverse of a matrix, determinant goes to the denominator. So determinant of this one goes to the denominator. Right? So this polynomial goes to the denominator, and then denominator of the transfer function will be this polynomial. In other words, eigenvalues of matrix A will play the same role as poles. So poles of G are included in the set of eigenvalues of A. Now, in some occasional cases, eigenvalues are even a larger set than poles. In other words, you may have a pole, you may have an eigenvalue, but you may not have that as a pole. What does this mean? In transfer function, maybe you are stable, but in a state space, you are not stable. What does this mean? This means, if I want to show you in a very simple example here, if you look at this system, we have a subsystem here, which is unstable, obviously, because it has 1 over s minus 1, and another subsystem, which is stable. This one has one pole, which is unstable, and this one has one pole, which is at -1 and is stable. Now, what is the transfer function from here to here? You need to multiply these two. When you multiply, this will cancel with this one. And then you only have 1 over s plus 1. So transfer function is telling you, I only have one pole, and it's stable. State space says, no, I have two eigenvalues, one of them is unstable. So this system is internally unstable. So state space, and this is one of the advantages of a state space, because it really includes everything inside the system. Transfer function might occasionally ignore something. These cancellations happen. In physical systems, normally unstable cancellations do not happen, as far as I know. But there could be cancellations happen in a physical system which are not unstable, but which are close to instability. Okay, now let's practice this state space for the DC motor equation. In this chapter also I will consider DC motor as the main example. So you remember the equations of the DC motor? We had one electrical equation and we had one mechanical equation, right? And then we said EA is K into omega, and tau is again another K into IA. Okay. Now, if you consider these two equations, both of them are first order, so they satisfy the condition. And one of them is derivative of IA, one of them is derivative of speed. So let's define one of the state variables as the armature current, one of the state variables as the machine's speed. Okay, if you define that, and then you have two equations, put them together in a matrix form, you will find A, you will find B here multiplied into U. And in general, if you have disturbance in a system, there will be another term added here. There could even be another term added here. So in a state space, we have very extensive way of modeling the disturbance as well. So A is this one, B is this one, BW for the disturbance is this one, C is 0, 1, D is 0, DW is 0. And the state variables are IA and speed. Input U is the armature voltage, disturbance is the load torque, and the output is the machine's speed. So again, everything you should be able to define. What is the input? What is the output? What is now the new thing we have here is the state or a state vector. And every element of that state vector, we call it a state variable. We can find the transfer function if you want, just to check, because we already defined the transfer function. We evaluated the transfer function. So just put into this equation C into Si minus A inverse B plus D. So C into this one inverse B. So you need to calculate the inverse of this matrix. So determinant goes in the denominator, and then you multiply, and then you will get transfer function. So this is the transfer function from the command, from the input to the output, to the frequency. If you want to find the transfer function from the disturbance to the output, you only put BW here. The only difference is that instead of B, you put BW here. And that gives you the transfer function from disturbance to the output, which is this one. Okay, so this is basically the core of a state space concept and a state space modeling. Now, if you have a system that you model that, a linear time invariant system, as a state space description or state space model, so it has output, it has a state vector. The concept of a state feedback says if the state of this system contains all the information about this system, why shouldn't I feed back that state vector rather than the output feedback? Because output does not contain all the information. So what I will do, I will take the state vector, multiply into some k, and remember this k is also a vector or a matrix depending on the size of the u and x, and then you bring it back and close the feedback. This is the concept of a state feedback. Now if you look at this one, this structure, and go back and compare it with the virtual resistor that we discussed yesterday, right? Or the day before yesterday. This is the generalization of the virtual resistance. So in virtual resistance, we took output current, we multiplied by k, and brought it here. Here it says, don't take output, take the state. This is more general. So this is generalization of virtual resistance. And you remember virtual resistance was extremely helpful in stabilizing the converter. So in general, this is even more stronger than virtual resistance that we had there. This is stronger than that one. Okay, now let's see what it can do for us, this state feedback. Now that you close the feedback using this state feedback, your equations change to this one. So you see your A changes to A minus BK. And what really played the main role, we said they are eigenvalues of A. Now they are eigenvalues of A minus BK. If we can design K properly such that eigenvalues of A minus BK are in good locations, and then we'll talk about what is that good location, then we can really get whatever performance we want from this system. So now the question remains, can I find a K that can place the eigenvalues of this matrix at a given location or at any arbitrary location? This is the concept of, or the question of controllability. If the system is controllable, the answer is yes. If the system is not controllable, the answer is no. So what is that controllability? First of all, the definition of controllability, we say this system is controllable if for any arbitrary initial and final conditions x0 and xf and final time tf, there exists a control input u of t for all t between 0 and tf that transfers the system state from x0 to xf for any arbitrary x0, xf and tf. So that means any point on the space for the initial condition, any point on the space for final condition, you can find an input that transfers this one to this one within time tf. That's a very strong definition, right? So you can, it means basically you can move the variables of the system to any arbitrary locations that you want. So that is definition of controllability. Okay, now I'm going to state 3 theorems, and we do not prove them. These theorems are, some of them easy to prove, some of them difficult, but anyway, we don't need to prove them. But it's easy to understand them and easy to work with them. So the first theorem says this system that we just talked about is controllable if and only if this matrix B, AB, A to B, all the way to AN minus 1 into B is full rank. So all the this matrix, which in general it's a fat matrix, so the rank of this matrix should be equal to the number of rows of this matrix. Okay, like I said, we are not going to prove it. If it's a single input system, this matrix will be a square matrix. Theorem 2 says that this system is controllable if and only if the matrix B and lambda I minus k to any arbitrary location. So controllability, we defined it, and you can check whether the system is controllable or no, either here or here. This is really easy. Even MATLAB can do for you. If it's controllable, then you are sure that there exists a k that can place the poles at any arbitrary location. Alright, so there are 2 commands in MATLAB that solves and finds the state vector k, state vector gain. So one of them is Ackermann, A, B, and P. So you give A, you give B, you give the set of eigenvalues that you want. So you want the eigenvalues to be here, 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 here. So you put them in one vector, and then solves it and gives you the k. There is another command which is more general. This command does not work for multi-input, multi-output systems, but this one works for multi-input, multi-output systems as well. Okay. Now, if there is an eigenvalue, if there is one lambda, that the rank of this matrix is not full. One of eigenvalues, that the rank of this matrix is not full for that eigenvalue. That means that particular eigenvalue, you cannot move it using a state feedback. Now, if that eigenvalue is already on the stable region of the complex plane or well stable, you say, all right, I cannot move this one, but I can move the others. But if it turns out that the one that you cannot move is on the right side of the complex plane, which is unstable, this is the worst case scenario. State feedback cannot solve your problem. So this is the concept of stabilizability. If there is an eigenvalue which is on the right side and is not controllable, we say this system is not stabilizable using a state feedback. Okay, really in practical systems you hardly come across a case that is not stabilizable or controllable. So for instance, for the DC machine, if you form B and AB, put them together, you get this matrix. Put them together, you get this matrix. Look at this matrix. Determinant of this matrix is k tau divided by JLA square. And this is non-zero. So this matrix is non-singular. It has rank 2. So DC machine is completely controllable. Now, when you close the state feedback here, so you change the poles or eigenvalues of the system, but you haven't still ensured that when you apply a set point to the system, the output becomes equal to the set point. So for that reason, we have a couple of ways to do it. This is the simplest way of doing it. You apply your desired trajectory here, or set point. You multiply into k0, And then there is this state feedback, which is internal state feedback, or generalized virtual resistance if you want. Now, if you want the output to be equal to the set point in the steady state, and assuming that this is a DC scenario, the desired set point is basically a DC value, not oscillatory like 60 Hz or 50 Hz. It means that you have to choose K0 such that the DC gain of this system from here to here is equal to 1. So you write the state space equations for this system with K0, and then you derive the transfer function, and you look at DC gain of this system. For DC gain, you need to put S equals 0, and choose K0 such that the DC gain becomes 1. So that's K0. Okay, so with this K0, now the output in the steady state will be equal to the input. If you want the converter to reach 10 kilowatt, it will reach 10 kilowatt eventually. Okay. However, the problem that this approach has is that if you look at K0, it is a function of C, D, A, B, all of them, A, B, C, and D, and K. K is fine because K doesn't have uncertainty, but A, B, and C, and D can have uncertainty. If they can have uncertainty, then you calculate this for the nominal values and then put it there, and then you run the system, you realize that you have a few percent error in the steady state. Sometimes, so x0 dot derivative of x0 is E. E is yd minus y, and y, or y minus yd, and y is cx plus du minus yd. So that's the first equation, and the second one we already have it, so put them together. Now this equation here, 4, 6, represents the state space equations of this augmented system. And for u is equal to negative k0 into x0, negative k into x. So negative k0 into x0, negative k into x, you can write it this way. And x bar is the augmented state. And let's call this k0 and k bar. So again, it's a full state feedback, the way we formulated here. In a state space, it's very important to formulate the problem correctly. If you do that, things really fall into place. So now you have a standard state feedback problem. You have a system with these matrices, and then you have a state feedback, so you can solve it. Just choose the location of poles and run the command occur or place, and then you will get the answer. And the first element of the answer is K0, the rest will be K. Okay, sounds like a very interesting approach and very comprehensive. Let's see what are the challenges with the state feedback. Challenges. So challenges, basically there are two, if you really think about that. One of them is that if you want to feedback the state, that means you have to have the state. So you have to measure the state. So you need more sensors compared to the only output feedback. There are ways to estimate the state. We will quickly talk about that to solve the problem. So that's also one approach, but it has its own weaknesses and strengths. The second weakness, you can say, or challenge, is we always said choose the location of poles, but how to choose them? That's not easy. Especially if you have more than one or two poles, it will be difficult. Up to 2 poles you can choose properly, no problem, based on those transient response, relationship between transient response and poles that we discussed the other day. You can choose the poles. But more than 2 poles you cannot choose. So like I said, the first one, the solution is using a state estimator, and the second one is the solution is using optimal control. In optimal control, then we don't worry about location of poles. We directly go and minimize a cost function. So let me talk about these two quickly. A state estimator. State estimator, the concept is this. If I have a plant or a control system here with these state equations, and obviously I have access to its input, to the output, but I don't have access to its state, and I don't want to put sensors. So can I design an observer or a state estimator that receives these two that I have, input and output, and estimates the state of that system for me? And if it estimates, then I can use this estimated state as the feedback. See here? Okay, let's see how we can design an state estimator. Obviously, if you want this estimator to have a good performance, this estimator should mimic the plant, should follow the plant. So why not put all the equations of the plant in the estimator? Okay, let's do it. So in the estimator, what we do, we put the equations of the plant. However, due to two facts, one, uncertainties, and the other one is the uncertainties, and the other one initial conditions. So because we don't know at what initial conditions the system starts, it's not necessarily zero. So due to lack of knowledge of that we need another feedback term to correct those errors, initial conditions and uncertainties. So this feedback term, if you look at that, it looks at the error, output error of this one, and it says I'm going to add this error to my state vector. Okay. We need to prove that this works. If you want to prove this works, you can show that the estimation error goes to zero. Estimation error, E, has this dynamics, x dot minus x hat dot, and then if you substitute from equations and simplify the terms, you will get this one, A minus HC into E. Now, if eigenvalues of this A minus HC are on the left side of complex plane and sufficiently left, then error will quickly go to zero. So we proved here that this estimator works. Because x dot equals AX. If A is stable, then all the state will go to zero. Now, in other words, we need only to design this H such that the eigenvalues of A minus HC are stable or sufficiently fast. How to do that? If you look at A minus HC, eigenvalues of A minus HC and eigenvalues of A minus HC transpose are equal, because when you transpose a matrix, its eigenvalues do not change. Now, if you transpose this one, it becomes A transpose minus C transpose H transpose. Okay? So, if you look at this one, is A minus a matrix known into an unknown matrix. So it's similar to A minus BK. Right? So the same approach, the same command, ACR command that we use to design K, now you can use to design H. You only need to transpose A and C first, and this is the way you transpose in MATLAB, and then choose the location of the eigenvalues of A minus HC or estimator, and then once you calculate it, transpose it. How to choose the estimator's poles? Well, the fact is that estimator should estimate the state variables or state vector and feed to the controller. And then controller, which is the state feedback, uses those estimations to close the feedback. Now, for that reason, it makes perfect sense to require that a state estimator or estimator it should be faster than the control, because it should estimate and then give to the other one, should be faster than the other one. How much faster? 2 times, 3 times, 4 times. So typical rule of thumb is 3 to 10 times faster. Okay. This is separation property. I'm not going to prove. It's not absolutely necessary, but it does it proves that, and you already kind of see here, but it says if you design K and H separately, is correct, no problem. In other words, you are not violating anything. K and H, you can design them separately. The design of K and H is separate. So you can read through the proofs. I don't want to take the time of the class with the equations too much. Okay, under what condition H exists? A transpose minus C transpose H transpose. So A transpose and C transpose should be controllable. Over there we said A and B should be controllable. Here we say A transpose and C transpose should be controllable. So this matrix should have a full rank. And this matrix, transpose of this matrix is this one. So this should have a full rank, because when you transpose, the rank doesn't change. This matrix is called observability matrix, right? And this condition is observability condition. So observability basically means that you can estimate the state from input and output, right? So mathematically, or the definition is, we call this system observable if the initial condition x0 can be determined based on the output measurement during a finite time. So again, we have here 3 theorems, very similar to the theorems for controllability. One of them says that this matrix should be full rank. If this is full rank, we already proved it somehow. If that is full rank, then the system is observable. The other condition says if C lambda I minus A is full rank for all lambda. And the third theorem, similar to the previous case, says if these conditions now are satisfied, you can find an edge that moves the eigenvalues to any arbitrary location. So if the system is observable, you can move its poles to any location you want. The case that it may not be observable is if one of the eigenvalues here, the rank of this matrix, is not full. Then that eigenvalue, that particular mode, you cannot estimate. And especially again, if it's unstable, this is a bad situation that you cannot really do anything about it. So you need to use a sensor. And detectability is similar to stabilizability. So if there is an eigenvalue which is on the right side of complex plane and you cannot estimate it, it's not observable, then the system is not detectable. Control terminologies. Okay. Example, for instance, the DC machine, if you form C and CA, it becomes this matrix. The determinant of this matrix is negative k tau over j, which is non-zero, so this system is completely observable. Okay, so that's a short discussion about state estimation. Now we go to the other challenge, which was how to choose the location of poles. We don't know if there are many poles, how to choose them. Optimal control basically goes around this challenge and solves the problem in a different way. In other words, it even changes the statement of the problem. It says, I don't want to find the location of poles. I don't care initially, or at least directly, about location of poles. Let me define a cost function which is reasonable, or I can make sense of it, and then minimize this cost. In other words, can I design a state feedback that minimizes this cost function? Then it has to put the poles in a good location. In other words, even in the best location, according to that cost function. if it has only one solution, and if you can find that solution, then the poles are in the best location. So what it does basically, it says, for instance, let's say start with this system, right? And this is the initial cost function. Let's say start with this cost function. And then we want to find k that minimizes this cost function. And here is 0. Okay. This is called linear quadratic regulator LQR problem. So we want to find a state feedback that minimizes this cost function. What is this cost function? If you look at this cost function, it uses transpose into some matrix into the vector. So this is generalization of a square. Square of a variable, when you take integral of that, generally speaking or physically speaking, it's an indication of the energy of that variable, right? So it says, I want to minimize the energies of all the variables in this system, including even the input. Give me k. What is the k that minimizes during these transients the energy loss or energy variations in all state variables and in the input? In other words, do not cause any unnecessary oscillation, because any unnecessary oscillation will add to the energy. So when you minimize it, it says without causing any unnecessary oscillation, give me the solution that is there. Okay, makes sense? Because this is very important to be able to make sense of this cost function. Now, if you can solve this problem and find k, we should be very happy with that. And then this q and r, these are the weight matrices, weight factors. These are should be positive definite. R should be positive definite if it's a matrix. If it's a scalar, it should be positive. Q should be positive semi-definite, means that it doesn't have to be full rank, but it should be positive. In other words, when you minimize a positive factor of the square of the variables, not a negative factor. Just doesn't make sense. Okay, so here is a little definition about positive definite and positive semi-definite. If you don't know, just read through. Okay, so if you choose Q as a diagonal case, and let's say U is a scalar, we only have one input, so the equation or the cost function becomes this. So like I told you, this indicates energy of x1 with a weight factor of q1. This indicates the energy of x2 with a weight factor of q2, and so on. And this indicates the energy of u. If you recall, if you realize, I put this one equal to 1. That's no problem, because when you minimize something, you can minimize a factor of that thing. It doesn't cause any problem. Just to simplify the problem, I put 1 here. So now you need to choose q1, q2, qn. These are positive or 0 numbers, and then solve this problem. How to solve it, we'll talk about that. Okay? And now each one of these q1, q2, qn shows the weight factor of the energy of that variable. In a physical system, we know what variable is more important for us, so we can put more weight on that one. What variable is less important? If there is a variable we really don't care, you can put 0 on that variable, and so on. We'll do a lot of practice on this one in the next few classes. Okay, so it looks like again a very good concept. So, but what is K? Does K exist? And if it exists, how I can find it? This theorem really summarizes the answer to these two questions. It says, write the matrix Q as Q1 transpose into Q, Q1. If A and B is controllable, even stabilizable, and Q1 and A is observable, even detectable, then there exists a K. So the condition on existence really now is to check whether A and B is controllable and Q1 and A is observable. If you check these two, and you can easily check these two, then K exists. Okay. How to find it? You can find it by solving algebraic Riccati equation. That's this one. So it's a nonlinear equation. You find L here, and then once you find L here, you put it here, and then it gives you K. Okay, so that nonlinear equation, sometimes it's easy to solve, sometimes not, but anyway, you don't have to solve because MATLAB has a very good engine for solving this one, and the command in MATLAB is this one. LQRABQR. So if you know A, you know B, you know Q, you know R, you just run this command and gives you K. Okay. All right. Now, this, yeah. Yeah, we will discuss those in much detail, but there is a lot of room for research. Just keep that in mind. Yeah. Okay, so now this linear quadratic regulator, LQR, was a very special case that we want the state variables of the system to go to 0. What about tracking? Because in practice we are interested in tracking. We want the state variables to go to some non-zero things. So for tracking, let me go to this scenario here. Okay, this one. For tracking now, let's say we want this y to track yd. So we put this structure, integrator, k0. We said that this is a very good structure because it will push the error to 0 because we inserted the integrator here. And we wrote down the equations of this system. Okay, so these are the equations of the system. And it has this state feedback. Can we apply LQR to this system? Not directly, because still it has two additional terms here, which we did not have in the LQR problem. So not directly. Can we modify the statement of the problem or the approach to solve this one? And this was basically one of the contributions of our lab to solve this problem for tracking. So the way to do, and I'm going to again skip this one, read it, because I prepared the students why it is a challenge and things like that. Okay, let me see where I defined it. I think I probably missed one page. Okay, yeah, it starts here. Sorry, it's all right. So this one. Now LQT designed for step commands, and we have different cases. We have step commands in power system or sinusoidal. So I will discuss both of them. Sinusoidal maybe not in this chapter, but when we go to inverters, I will discuss that there. So let's say YD is a step command here. It's a DC system or a three-phase system that you converted to DC. Okay. So in this case, we propose to apply d over dt, which is derivative operator, to both sides of these equations, this set of equations, this one and this one. If you apply that, this yd is a step function, this disturbance is a step function. When you take derivative of them, both of them become 0. And then now you have derivative of this. Let's call derivative of x equal to z. and derivative of u equal to v. So you will get these equations. Z dot equals a bar z plus b bar v, and then v is derivative of u, which is derivative of this state feedback, so becomes k bar into z. So now we converted that problem into a regulator, LQR problem, regulator problem, using this approach. Okay, so what do you want to minimize here? Let's look at z. If you look at z, z is derivative of x. Now remember, x was what? X was, the first component of x is this one. So derivative of that becomes error. So the first element of z is the tracking error. At least I know that. So if I choose my Q, my matrix Q, such that the first element is non-zero and all the other elements are zero, then I will get Q into tracking error square plus V square. And V is d over dt of u. So it's rate of variations or rate of change of the control signal. So this cost function minimizes at the same time the energy of the tracking error and the energy of the oscillations or rate of change of the control input. It's a very interesting cost function. So in this case, Q is this one, very simple. Q 0, 0, 0, all of them 0. And then R is 1. Only have one control parameter, Q. And then you can solve it. Does the solution exist? I mean, I have proven here that the solution exists. Yeah, that's the proof, very simple. And I think I referred to some of the papers we had. But now let's go to this example, DC motor. In DC motor, we realized A is this one, B is this one, BW for the disturbance. And then now A bar is this 3 into 3, B bar is this one. So you only have one parameter Q, and then you need to run LQR of A, B, Q, capital Q, and R. R is 1. Now increase Q, that lowercase q, and then see what happens to the poles of this system. If you look, increase Q, what happens to the poles? The system has 3 poles, and these 2 poles or eigenvalues move towards each other, these 2, and then separate and go this direction, and the third one goes this direction. So for every value of Q, lowercase q here, you have this scenario. Let's say you choose Q equal 10 to the power of 4. Then if you simulate the system and look at its response, that will be this. If you choose Q 10 to the power of 5, so you push the poles more to the left, so the response becomes faster. If you choose it 10 to the power of 6, it becomes even faster. But interesting things we realize is that the oscillation does not change. Make it faster and faster, but the level of oscillations do not change. Almost impossible to get the same thing using transfer function approach. Almost impossible, unless you are very expert to do that. If in transfer function approach you try to speed up the system system starts oscillating more. But here, because we are really getting the best solution, and that best solution minimizes all the oscillations. So we will get like about 5%, 6% overshoot. And the response, if you want to make it faster, you just increase Q. If it's sinusoidal, let me explain. I think I have a few minutes, no problem. If it's sinusoidal, then you need to, rather than inserting an integrator in the control system, you need to insert what we call second order generalized integrator, and that is this transfer function, this one and this one. So you will add 2 new state variables to your controller, And your controller now has two state variables, and its state space description is this one. Now you need to augment this one with the initial, with the plant, which becomes now n plus 2. That's this one. And this is the state feedback. Now, can we apply LQR directly? No, because these terms are there. How we can get rid of these two terms? Not derivative, we apply this one, because these are sinusoidal. But we know sinusoidal at what frequency. So if you apply this operator, these terms will go away, and then you will get an LQR problem. And interestingly enough, again, if you look at Z, the first two elements of Z, one of them is the tracking error, the other one is derivative of the tracking error. So you can minimize this cost function, a great cost function, because it has tracking error in it. You minimize that. It has variations of the tracking error. It gives you more freedom here now because the controller is order 2, and also energy of the variations of the control input. So it minimizes the expenditure of the control, so to speak, in the optimal control terminologies, and it minimizes the energy loss in the state variables. So your Q is now has two elements, this one and this one, Q and Q1, and your R is 1. You just go ahead and solve the LQR problem. Now you have two parameters to adjust, Q and Q1. In the previous case, you only had one Q. Here you have Q and Q1. We will practice this in several examples when we get to chapter 6, hopefully tomorrow. Or yeah, I think we can do it tomorrow. Hopefully, towards the end of tomorrow. Yeah. Okay. All right, I will stop here.